Welcome to today's lecture. So today is the day 3 for the 6th week. So let's see what did we learn in the last 2 or 3 classes. So we learned how to deal with so-called projection operator, which is used to form the symmetry adapted linear combinations or SALCs. So in the previous class, we particularly learnt about one particular type of projection operator, which we called as incomplete projection operator, which is formed by using the characters of the irreducible representations. Okay, so using that incomplete projection operator, which is sufficient for our purpose, we could form the symmetry adapted linear combinations of one molecule that we discussed in the previous class, that was ethylene. And we did that quite rigorously, and we mentioned that there are certain steps involved. The first step, you have to identify the point group of the molecule, and second, you choose the right basis. So in that particular example, we took the 1s orbitals of the hydrogen atoms, and we considered the sigma bonds, that is CH sigma bonds. So altogether 4 sigma bonds. We took this as basis functions, and with that basis set, we form a representation. So that is the step 2. And in the next step, we reduce that representation and find out what are the irreducible representation that it may contain. And after that, what we did, we carried out the projection operators based on all those irreducible representation that we found by reducing the representation gamma that we formed earlier on each of these basis functions. So we started with only one basis function, that was sigma 1, and we formed operated the 4 projection operators corresponding to those irreducible representation that we got, and ultimately we could get 4 sets of SALCs in terms of this basis functions, that is this sigma 1, sigma 2, sigma 3, sigma 4. Okay, so this particular example was shown for one-dimensional irreducible representation. So one-dimensional irreducible representation, using projection operator for one-dimensional irreducible representation and forming the SALCs is pretty simple job, because you have one operation and one function coming out of that, and this one function means the linear combination of the basis function that you choose, and that obeys all the symmetry properties of that particular irreducible representation. And I also asked you to find out whether this combination that you are finding, do they really transform as that particular irreducible representation that we form the projection operator. We use the projection operator for that particular irreducible representation, meaning that this combination of all sigmas, getting sigma 1, sigma 2, sigma 3 and sigma 4, adding all of them, whether this particular linear combination really transform as the this will be AG representation or not. Okay, so this will be AG. So when we move to with higher order irreducible representation, that means with higher dimensions, for example like 2-dimensional or 3-dimensional, things will be little more harder, and we will see right away how to deal with these 2-dimensional representations or 3-dimensional representations. So the next example that we will take is the case of square planar complex PTCl4, okay, having their usual charge, which we will neglect for our purpose. So the first step is to identify the point group symmetry. So for the square planar complex, it is D4H, right? You should be able to readily find out the or identify the point group of any given molecule right now. And then we have to choose the basis function. So here also we will consider this 4 sigma bonds. So this 4 sigma bonds taken to be sigma 1, sigma 2, sigma 3 and sigma 4, and we will use these as my basis functions. So my sigma 1, sigma 2, sigma 3 and sigma 4 will constitute my basis set. Alright, so that was my step 2, and it is still not complete. So using this basis set we have to form a representation, fine. So that representation most likely is going to be reducible, because we are using this 4 basis functions, and you will find out that it will be reducible representation that you will get. And once you get this representation based on this basis set, you consult the character table for the particular point group D4H, which is given here. So you get the character table using this one and utilizing the formula that we use to reduce reducible representation into the irreducible ones, you get the irreducible representations. So if you do that, you will find that your reducible representation that you form out of this basis set will give you A1G, B1G and UU as the irreducible representation. Alright. So here I have 2 one-dimensional irreducible representation, A1G and B1G, and 1 two-dimensional representation. Okay. So for one-dimensional representation, things are as usual that we have already discussed in case of ethylene. So here also you should be able to do that very easily. Okay. So here there is a mistake. This will be A1. Okay. So specifically this will be A1G. Now you can find out the SLCs for this one-dimensional irreducible representation A1G and B1G using the respective projection operators, which is very straightforward and easy. Now next we will go after the two-dimensional SALC. So the two-dimensional SALCs will transform as the EU irreducible representation corresponding to D4H point group. Okay. So here if you look at the character correspond to the EU representation for D4H point group, you will see that only the operations identity C42 I means inversion and sigma H have non-zero characters. So when you find out the SALCs, when you operate the projection operator, you have to look at the effect of all the symmetry operations on this particular function that you have. Right. So since we are dealing with the incomplete projection operator where we deal with the characters, and if there are symmetry operations which gives the character as 0, then we really do not care about them. So take only those symmetry operations which gives non-zero characters. So here these 4 symmetry operations will give us non-zero characters that we can find from the character table. So that we consider, and with that we form the projection operator and operate on one of these basis functions, let's say sigma 1, and then what we get? We get this sigma 1 minus sigma 3. So here we jumped a few steps, so you can do everything thoroughly and you should be able to come up to this particular point. Okay, that is the symmetry adapted linear combination as sigma 1 minus sigma 3. Now I got one particular SALC. Now EU is a two-dimensional irreducible representation. Therefore, for a two-dimensional representation, we need two orthogonal functions, correct? Because all the orthogonal functions will, rather orthonormal functions will be forming the basis for all these irreducible representations, right? And for two-dimensional irreducible representation, I need two such orthonormal functions. So normality we will take care later, but first we have to have two orthogonal functions. So these two orthogonal functions will transform together as the say EU representation in this particular case. So we have got 1, that is sigma 1 minus sigma 3, neglecting the normalization part. So we need the counterpart, right? So here we mention one thing, that any member of a set of function that form the basis for a representation must be affected by the symmetry operations of the group in one of the two following ways. What are those ways? First one, that is the function will go into plus or minus 1 times into itself, right? So upon the symmetry operations, it will either give back the same function, or it will give back the function with a coefficient of -1. Second, it will go into another member of the set or a combination of the member of the set. So that also we have learned earlier, that it can act as the basis function itself, or it can if it is like if one forms a linear combination of several basis sets, then also that can work as a basis for the irreducible representation that is under consideration. Okay, so if we look at the effect of the operations, that is E C2 2 C2 prime I and sigma H and 2 sigma B, we see that they give this plus minus sigma 1 minus sigma 3. So we take that SALC that we got first, that is sigma 1 minus sigma 3, and here when we operate all these symmetry operations like identity C2 C2 primes I or sigma H and also sigma B, they give either the plus or -1 of this already obtained symmetry adapted linear combination. So that is not surprising, but at the same time this is not informative. Okay? It doesn't tell me anything new. So I need to find out what will be the other function which will be orthogonal to this existing sigma 1 minus sigma 3 and jointly form the basis for EU. So we have to operate the remaining operations, and thereby we can find the other functions. So we take that first SALC sigma 1 minus sigma 3 and operate the rest of the symmetry operations, which does not give back this sigma 1 or sigma 1 minus sigma 3 either plus 1 multiplied by plus 1 or minus 1, but something else. So when I operate C4 on sigma 1 minus sigma 3, I get sigma 2 minus sigma 4, and I get the same result, that is sigma 2 minus sigma 4, when I operate C2 or S4 or sigma D on that sigma 1 minus sigma 3 SLC. So therefore I have got the other counterpart, that means this altogether sigma 1 minus sigma 3 and sigma 2 minus sigma 4. These two set of SLC will form the basis for EU. Okay, so these are my right SALCs. Okay, so we have got this as orthogonal functions. One thing is remaining, that is we have to find orthonormal function. So the requirement of normalization will give us the normalized SLCs, which is given as 1 upon root 2 into sigma 1 minus sigma 3 and 1 upon root 2 sigma 2 minus sigma 4. Alright, so this is pretty straightforward to normalize these functions. So that's how we got the SALCs that we can form by using projection operator for two-dimensional irreducible representation. All right. So next we will move toward even little higher a case where little bit complication limit is little bit higher. So we will look for a case which involves a three-dimensional irreducible representation, and we will try to find the SLC for that particular three-dimensional representation. So we'll consider a molecule, a hypothetical molecule, say MH6. So here this MH6 has an octahedral geometry, and all the MH bonds are equivalent. So this surely belong to the OH point group. So while dealing with this problem, you must have the character table for OH point group with you. So here the OH point group, the character table for OH point group has been given. So you notice how many total number of symmetry operations are there. So you have like 9, 6, 15, 21, 24, 25 and 31, 39, 42 and 48. So altogether there are 48 symmetry operations. So things can things may seem to be pretty complicated at the beginning, but as you will go ahead, you will see that things are not so complicated as it seems initially. So after finding the point group to be octahedral or OH, what we need to do? We need to form the representation, right? So after you get the representation, you reduce them, and here one thing is important to note, that you don't need to really consider all the all the operations, that is like 48 operations that are involved, but you can actually select the particular subgroup which comes out as O. Okay, from OH you can get a subgroup of O. So you use the symmetry operation corresponding to that particular group O, and your job will be done. So here in solving this particular problem, we have used that particular approach, and we form the projection operator and then apply on the basis functions. All right. So what we have got? So for we have like if you look at the character table for OH here, you will see there are three-dimensional representations. Okay, so it's like T1 and T2 and both G and U. So you get the symmetry adapted linear combinations for T1 irreducible representation when you operate on any of these functions. So you first operate on sigma 1, which is one of the sigma bonds, MH bonds, and you get this to start with, and when you operate on sigma 2, you get another one. Okay, so if you subtract one from another, okay, so what you get? You get sigma 1 minus sigma 2. So if you keep going in the same direction, so you can operate projection operator on sigma 3, sigma 4, sigma 5 and sigma 6, and ultimately you can get the SLCs and then normalize. So you get the orthogonal functions. So you get the ultimate orthogonal function, because see, this and this ultimately should be orthogonal. So until unless you get the orthogonal functions, you have to try orthogonalization, and thereby here you use this subtraction. So where you subtracted this first combination and the second combination from the first one, and you got this function sigma 1 and minus sigma 2, and in this way if you form the whole thing, the whole set of combination by operating a projection operator for T1 on all the basis functions, and you get several combinations, and then you perform the orthogonalization, and you ultimately get in terms of sigma 1 minus sigma 2, or sigma 3 minus sigma 4, and sigma 5 minus sigma 6. And when you incorporate the normalization condition, you get the overall normalized orthogonal functions that will form the basis, that will together form the basis for the three-dimensional representation which we are considering here. All right. So now we'll go to some some other molecule general where we may encounter one-dimensional, two-dimensional, three-dimensional, and here we are going to consider one particular molecule which is PF3. Now in the last class we mentioned that we may actually have some problem, particularly when you have the equivalent atoms, and that is because that each of the atoms or the basis functions will contribute to the MOs. So in case of PF3, when we set out to form the SLCs, first we have to choose the basis functions. Now here you see that the two axial PF bonds are equivalent, while the other three equatorial PF bonds are equivalent. Now this axial and equatorial PF bonds, they are not equivalent, so I have to treat them separately. So here actually this shows an example where you have to be careful when you want to choose the basis set and then do the rest of the work. So here we take the sigma bonds as my basis functions, true, but altogether I will not form the basis set as sigma 1 to sigma 5. Rather what I will do, the sigma 1 and sigma 2, which corresponds to these axial bonds, axial PF bonds, I will form a basis set out of these two, while the rest three sigma bonds in the equatorial plane, I will use, I will form a separate set and use them as another basis set. So I got set 1 and set 2. So next step I have to form the reducible representation, and then in the next step we have to reduce it. So I have to do it for both the basis sets. So I do it for set 1 and as well as set 2. So here we get the representations which we are writing as gamma 1 2, meaning that this gamma is formed by taking sigma 1 and sigma 2 as basis functions, while the other representation we are writing as gamma 3 4 5, meaning that we are forming this representation using the basis set comprising of sigma 3, sigma 4, sigma 5. So upon reducing gamma 1 2, we get it as A1 prime plus A2 prime, and from gamma 3 4 5 we get A1 prime plus E prime. All right. So here we have one dimensional as well as two dimensional irreducible representation. Now first we have to get the SLCs for the one dimensional representations. So we start applying the projection operators for the particular irreducible representation, that is A1 prime or A2 prime on the basis function say sigma 1. So when I operate this projection operator for A1 prime on sigma 1, I get this sigma 1 plus sigma 2, and when we normalize, then we get the corresponding normalization factor. Easy. So same thing is applicable on this projection operator for A2 prime, and we get the corresponding normalized SLC. Now when we apply it on sigma 3, so we form a basis for E prime, we form a projection operator for E prime, and then we get a function, orthogonal function, and we normalize this and get another SLC. And when we operate on sigma 4, we get another SLC. Now this P projection operator for E prime, that should ultimately give me two functions, right? So now altogether I have got so far 4. but I should get altogether 5 SALCs, correct? Because it had 5 basis functions, so I should have 5 SALC. So we should get another basis function which will be orthonormal to the one that we are getting here or here. Okay, so if we find that out, we should get another SLC like this one. So this one I am leaving up to you to how to find that out. Okay, how to orthogonalize and then ultimately find out this fifth SALCs. So I will request you to try this one out later. So what did we learn today overall? So we used projection operator to find out the SALCs corresponding to one-dimensional, two-dimensional, and three-dimensional representations, and also we looked at a molecule which has two different sets of bonds, and which suggested us that we should consider two different basis sets. So instead of forming only one representation, we formed two representations, reduced them individually, and then formed the projection operators, use the projection operators on those individual basis functions, and got the symmetry adapted linear combinations. And ultimately we saw that okay, we could get 4, but then we said that okay, using the concept of orthogonalization, you can find out the fifth one, which has to be there because the number of basis function and the number of SALCs should be equal. So with this I will stop here today, and in the following class we will come back with some of the applications of this SALCs, because see, we are forming this SALCs because there is a definite reason. At the beginning we said that whenever we consider a bond formation, we have to find out the certain orbitals which will combine, and it will give rise to a molecular orbital which will maintain the symmetry of the forming molecule. So after knowing these SALCs, we should be able to get some other information. So for example, the energy levels of the molecules, and that means the orbitals, and how these orbitals are occupied in a molecule. So we will try to learn those things in the following class. Okay, till then I thank you for your attention and have a good day.